Thanks, Gautam, and good morning, all.
Hang on. We all clap loudly.
So I think our topic is little controversial. We are questioning claims. You must be thinking why you really need to question databases, right? It's already evolved and it's scaled, and almost everyone is using it, right? And before I go deeper, right, I will just introduce. So I work as an architect at NPCI. I take care of distributed systems and blockchain. And I and Sarthak worked on a database project. Basically, we built a strongly consistent distributed key value pairs or a storage engine similar to that. And when we think, right, how you build databases or how you understand which database is right one, right? So I know that most of you might have chose a single database, right? Either Postgres or MongoDB, or maybe the traditional relational DBs like, right, MariaDB or MySQL or something, right? And when you see NPCI, right, we also evolved over the period of time. We started with Oracle database, and then we moved to Postgre, and then we moved to Cassandra. At some point, we realized that at our scale, when we process 21K TPS, right, peak TPS every second, so we realized that we can't really have a database in a critical path. So we came out of a database mode to purely processing in memory. And then we introduced UPI Lite. So when we introduced UPI Lite, the problem was you need a very consistent database, which is 100% durable, which supports a good fault tolerance, and it has the scale and distributedness in it. So we started going deeper into each and every aspect of database to understand that, okay, whether any of the existing database really works, the way they claim, the way it is implemented, and will it really suit for our own needs. So that was the reason we went inside, and we thought okay, we will share the same insight to everyone. When you're choosing a database, right, rather than blindly choosing a database, you start understanding what is really inside, whether the claims are really right, or how it is actually behaving in the production environment when it comes to a scale or a highly scalable applications, right? So that is what we are going to cover. Maybe Sarthak will start on the aspects how the design patterns are there, how the storage engines are designed, and how database actually works deep inside. Yeah.
Thank you, Titu. Hey, folks. Good morning. A little louder, please. Good morning. Let's try it one more time. I have few seconds. Good morning. So my name is Sarthak. I'd worked with NPCI for building a strongly consistent and a distributed key value database in Go. I'm passionate about database internals and stateful distributed systems. I'm also a contributor to a book called Patterns of Distributed System by my colleague. And following my own passion, I conduct a couple of workshops on refactoring and storage engine internals. Okay. It's a very simple talk. All we'll do is three things. We'll understand some patterns of storage engines. Once we understand the patterns, we'll question variety of database claims. For example, durability, read optimization, write optimization. And in the end, we'll pick a database that fits our use case. We have a couple of use cases. So let's start. Like I told you, it's a very simple talk. We'll start with identifying the icons. What can be simpler than that? You worked with a lot of databases, right? Yes or no? Yes. Identify different databases or key value stores in this slide. Quickly. Louder. BoldDB, very nice, Gautam. Thank you. Louder, please. Cassandra, very good. Cockroach, yes. What else? There is Badger. Someone said Badger, very good. Oh, Aman, thank you. Aman is from Badger. What else? What is this leopard-looking thing? It is RocksDB. Thank you. RocksDB is a key value store in C++ by folks from Facebook. See, while we are on this slide, I'll quickly tell you, a key value store only deals with keys and values, right? For example, Redis, Rocks, Pebble, Badger, all these are key value stores. Most of the modern day databases are built on top of key value stores. For example, dgraph uses Badger for storing and retrieval. MyRocks uses rocks for storage and retrieval. Yugabyte uses modified rocks for storage and retrieval. So before we move forward, let's quickly understand what a pattern is. We heard this term yesterday as well. A pattern is a repeating or a recurring solution to a common problem. That's it. So once you understand the patterns of storage engines, you will be in a position to question database claims and pick the right database or databases for your needs. That's it. So the first pattern, persistence. See, persistence is all about ensuring that once your data is written and acknowledged as stored, it can never be lost. That means, once a database says, hey, I've written your data, it will never be lost. It's a thing with persistence. Persistence includes two things that databases have to do, technically. One, write-ahead log. Write-ahead log is an append-only log. So if you see the image below, client is trying to write a key value to a key value store. It can very well be a database. That change will be written to an append-only log file called write-ahead log. And once it is written there, it will be written to KV's state. That could be a hash map, B tree, binary tree, does not matter. Write-ahead log gives you durability and recoverability. In case of crash, your write-ahead log will be read and the state will be replayed. Now, fsync. All of you have done file.write? Yes, no? All databases will do file.write because that's their job, right? Yes, no? Yes. So what happens when you do a file.write? Does the data actually go to the drive? That means your underlying disk, or does it go somewhere else? Which cache? Disk controller is a hardware. Where does the data go? Sorry? Page cache, that's right. When you do a file.write, sir, in standard I/O, this data goes with OS kernel page cache or OS page cache. The data does not go to disk. There is a separate system call called fsync that flushes these changes to disk. So when a database claims I am durable, right? The first question that we'll ask is, hey, do you implement a write-ahead log? Simple. Do you do an fsync? Because if you're not doing an fsync, the data will only be with OS page cache. And yes, OS will periodically flush the changes. But that does not mean 100% durability. With me so far? If fsync is performed, we need to ask, hey, do you perform an fsync after every write, or do you batch those fsyncs? Or do you schedule those fsyncs? Because if you're scheduling, that means there is a chance data could be lost. Okay, quickly. I have a few icons, Postgre, Rocks, Bolt, and Mongo. Are all of them durable? Postgre, durable, yes or no? Yes, very good. Rocks. If you have seen or heard of rocks, but it's a Boolean value. Pick one, yes or no? Yes. Bolt. Yes. Okay, then default value is yes. Mongo. No, okay. See, Postgre is durable, 100% durable only if you turn fsync on. Postgre gives you an fsync option. Unless turned on, you're relying on OS page cache. Same with Rocks. Rocks gives you an fsync as a part of its write options. Bolt DB. It is a key value store written in Go by Ben Johnson. The repository is archived. It does an fsync after every transactional commit. And Mongo doesn't do it. It relies on a property, sync period seconds, which is a scheduled fsync. Remember this. So when you need 100% durability, you need to question write-ahead log and fsync. Good so far? Okay. Efficient retrieval, second pattern. It is all about implementing data structures to minimize latency for disk reads. See, disk reads are expensive. Hard disk reads on an average take almost 8 to 10 milliseconds. That's too much of a time. You need to have data structures to minimize read latencies. You could also cache the data, that is all right. So first, a B plus tree. Anyone heard of it? Yes, good. What is it? It is a self-balancing ordered tree. That means every node in a B plus tree contains multiple keys, and each key is ordered. That means every page is sorted by keys. And every page will contain k plus 1 child pages. That's it. The values lie in the leaf page. It is a read-optimized data structure because the height of a B plus tree is small, even for large amount of data. Why? Because you're fitting multiple keys in one node. I'm using the term node, however, that is a page, typically sized 4 KB or 8 KB. If the height is less, I have to read lesser number of pages from disk. So first, if someone claims, hey, I'm read optimized, first question would be, hey, do you use a B plus tree or its variant? Second, what if I don't have to read the data at all? That's where Bloom filters could come in. A Bloom filter is a probabilistic data structure which can tell you whether the data is present in the set or not. It can give you one of the two possible answers. Definitely not or a maybe. For example, if you have to read a key from a file of size 1 GB, one option is to scan the file piece by piece. This piece is called as a block. Second option, ask Bloom filter. Hey, Bloom filter, do you think this key may be present in a file? It's a probabilistic data structure. If the key is not present, it will tell you, hey, it's not present. Don't waste your time going through the file. If the key may be present, it will tell you maybe, hey, I'm not so sure. You can go and check for yourself. So you can go and read the file. How you read is a different matter. So when it comes to read-optimized claims, the first question is obvious, data structure. Do you use a B plus tree or its variant? Do you cache disk blocks? That means file is organized on disk in blocks which are fixed size. Do you cache blocks? What is the block size? What is the eviction strategy? Do you use a Bloom filter so that you can skip going through unnecessary files? And finally, how do you order the data in files? Do you keep the data in blocks of files in sorted manner? Because if they are sorted, when you read the blocks, you can do a binary search. Fair? Yes, no? Okay. Then quickly, which of these is read optimized? I'll tell you, Bolt is a KV store in Golang built on B+. Mongo uses wired tiger, a form of B tree. Rocks uses LSM, but it does use Bloom filter. So are they read optimized? Yes, no. All three louder. Okay. Bolt, B plus tree, read optimized, minimizes disk latency, fair. Mongo, wired tiger variant of B tree, read optimized, fair. Rocks is an LSM based storage engine, we'll get to that. It does use Bloom filters. That does not mean it becomes read optimized. These are the options for making your system avoid going through additional files. We'll see that. Rocks uses Bloom filters to avoid files which are definitely not going to contain the desired key. But Rocks is not read optimized. Okay, the last pattern. Like we saw retrieval, now it is time to write. It is all about designing data structures to minimize write latency. Fair? Now, like B plus tree is a read optimized data structure, LSM is a write optimized. Now, before we get to LSM, the idea behind a write optimized KV or a write optimized database is to do sequential I/O. Remember, sequential I/O is writing to a file one after the other. You write, then you write the next block, then you write the next block, and so on and so forth. A contiguous write or an append-only write or a sequential write is much faster on hard disk than a random write. Similarly, a sequential write is faster on SSD than a random write. However, the difference is not as high as it is in SSD. So any database or a data structure that claims I am, write optimized, the first thing is it might be doing a sequential I/O, point one. Second is LSM. The idea behind LSM can be summarized in 2 lines, because that's all the time I have, is it takes the data, which is, let's say, a key value, write to a write-ahead log. Once it writes to write-ahead log, it will write the data to an in-memory store, which is a buffer. This buffer is typically called as memtable. Like someone was talking about Z set or Z set in Redis, they are built on skip list. Same way, mem tables are built on skip list, layered linked list which are sorted in order. So LSMs actually write the data in memory after writing the data to wall, and once in-memory buffer is full, they flush the data to disk. Very simple, at a very, very high level. On-disk files are called sorted string table files. So when someone says, hey, I have a database that is read optimized, or I want to pick one for read optimization, first question, do you use LSM? I'll leave the second part aside. And do you use or do you perform sequential I/O to disk? If the answer to these questions is a yes, the database or a key value store is write optimized. That means it can handle write versus read ratio which is skewed towards write. Okay. RocksDB, Cockroach, Cassandra, Bolt, and Badger. Are these write optimized? Rocks is write optimized, fair. Badger is. Cassandra is right. Cassandra uses LSM. Rocks uses LSM. What do we have? Cockroach uses LSM. Cockroach is using Pebble, which is LSM. Badger is LSM. And Bolt DB, which is a B plus tree based. It is not write optimized. Fair? Okay. So we have patterns, we have claims. Now we need to try and see if we can apply these patterns somewhere. We have 2 use cases. First, an audit log. Let's imagine that we have to build an audit log. We are not going to build a fancy audit log. We just have 3 requirements. I need 100% durability. I need a higher write ratio. Write versus read is skewed towards write. Clear? A louder yes would help. And append-only log, fair, which is a side note. Can you translate these to some claims, or before claims, can you translate these 2 patterns? What is it that we need? 100% durability. Faster, quicker, whatever. F-sync किस पे करोगे? Wall पे. So we need write ahead log and F-sync. Good. Higher write ratio. LSM, what else? Sequential I/O. Append-only log is hidden inside this because write ahead log is an append-only log. Okay. Fair. Good so far. What will we pick? I need a single node database or a single node KV. We are not going distributed. Single node. Quicker. So Gautam actually told me he'll give a party for right answer. I didn't ask if there is a party per right answer, but you can ask him. Quicker. Rocks with F-sync on, right? There is a property. If you need 100% durability, you need to turn it on. So rocks ka equivalent is also fine, let's say pebble. If you can guarantee that there is an F-sync either on, or the option is given, or default it is on. If you want to go distributed, you can have something like a red panda, which also does an F-sync on each write, transactional. Can I pick Mongo or Bolt? Why? Okay, not write optimized. Anyone from here? Correct. Bolt is durable. Okay, Bolt does an F-sync on every transactional commit. Fair? Configuration management. I need to build a single node configuration system. Configuration is a key value pair. Once the data is written, there will be a lot of reads. Read versus write ratio is skewed towards read. Good. Bolt DB, 100% durability. So I've given B Bolt. 2 reasons. Bolt is archived. And Bolt does not implement write ahead log. B Bolt was built on top of Bolt. B Bolt was by folks from etcd, Google. So it does give you durability. It is built on B plus tree, supports transaction, and it can support writes which are frequent, smaller than 200 bytes. Can I use rocks or Badger? Yes, no. We need read optimized, right? The reads versus write ratio is skewed towards reads. I need a large number of reads, which means I need to minimize disk latencies in reads. Badger rocks are write optimized. You can use Postgre. The point is, configuration is a key value pair. Do you really want to use Postgre? You can definitely go with a write optimized with an index, sure. So that's it. Like I told you, a very simple talk. Understand patterns. Let me finish. Understand patterns, question claims, and pick database. Don't take claims on their face value. Learn to question them. In order to question, you get to have some basic building blocks, and these are your patterns. Thank you.
All right, I haven't even said that we have time for questions, but there's a hand raised, so we'll have to take one.
Do column-based databases use B plus trees? I'll give you an example. Say ClickHouse is a column-based database, and it uses a lot of skip indexes. So does it also use, internally, does it use B plus trees?
So I'm not sure about ClickHouse, but yes. Every database for read optimization has to use a B plus tree or a variant of B tree or a variant of a B plus tree. For example, Postgre. How does it achieve reads? By building an index. What is the simplest index? A B plus tree. What is a key? Key of the table. What is a value? A pointer to a page. I'll not go there. But yes, if either the whole database may not be using B plus tree, that's all right. There would be pieces, for example,
indexes, keep
Postgre,
indexes maybe.
Right? Postgre is not a B plus tree based database. The data is organized in heap files, but indexes, simplest is a B plus tree.
Any other questions? All right, there is one more.
Are there any metrics that you guys would recommend for evaluation across this? So, like one simple thought that I have in mind, you can evaluate whatever, but Postgre is most probably going to serve 99% of the cases in 99% of the time, right? So, definitely if you want to use RocksDB or BoltDB, there will be cases, there will be a point after which it becomes useful, right? So, are there any such metrics that, okay, up to this point, yeah, just run with Postgre, right? Like everything is good in the world after that.
So, do you want?
So maybe one of the thing is most of the databases, right? It works to a certain scale. Like I told, right? We worked with Oracle and it scaled to some level. We went to Postgre. There are systems which runs on MariaDB also. There are systems which runs on Postgre. Like Zerodha runs 100% on Postgre. At some point of time, we realized that when it comes to the UPA volume, right? UPA handles 21,000 transactions per second, which translates to almost 120,000 requests per second. That's the scale which UPA operates. And there what we observed is like, the more scale or more the data coming in, right, you need a write optimized database rather than having a read optimized database. So we ended with Cassandra. So when it comes to Cassandra, it comes with certain baggages actually. I mean, the node size has to be very high and you need to have a very large pool and everything. So we reached to certain level where we realized that, okay, operating Cassandra at a scale of UPI is not feasible because of the infrastructure cost and other efficiency problems. Then we thought, okay, we will remove the database itself from the critical path of any transactions. And we go ahead with a pure in-memory processing. Like we use KeyDB and heavily use Kafka. So, I mean, Kafka is also not 100% durable, but still we manage it to a greater extent. I mean, scale is all about compromises. So what you can compromise at the right point of time. So that's how we handle. Metrics, what we identify is what is the write ops it can support, what is the read ops it can support, and what is my business requirement, and what is the latency it comes with when you perform each of the operation. And since it's a critical system, we consider some of the other matrices also, like can it recover faster, like when you do a fail safe, or maybe when you fail some of the nodes, right? Can it recover faster without having an impact on the overall transaction processing? Can it run active-active with a geographical distance across multiple data centers? Where I accept transaction from all the sites. So we identify these business metrics also when you design or maybe define a database for our use cases. Not just the performance, every database will work to a greater extent as long as your overall volume and your technical requirements are within that limits, all databases are good. But beyond that point, maybe you need to identify what is the right one for your own use cases. It comes with very specifics actually, I mean, how you implement your technology or how you implement your stack.
Thank you.
Were there any need to customize the Kafka or anything? Did you open source that?
Yeah, actually we customized most of the implementations, like even Postgre also, Cassandra also, we maintain our own versions internally. As of today, we have open source, but we are planning to open source it. So over the time, we will open source it, but there are custom implementations which is tailored for the need of NPCI. So whether it is Cassandra, KeyDB, Redis, Kafka, even Postgres, we customize heavily.
Yes, Harman?
Hey, for something like RocksDB or PebblesDB, how do you do the DB backups and how do you go distributed in that kind of a system?
So Rocks and Pebble, as far as these examples are concerned, they are embedded key value. Yeah. They are not distributed, okay. So you can consider them as single node. The better choice is embedded. Now, if you were to either build a database or pick a database that is distributed, that means your database layer has to be sitting on top of, let's say, Rocks or Pebble. That will be a single node DB. Fair? Let's say I build my Postgre, which is on top of Pebble. Okay. Next is distributing it, which essentially means your database will have to either support sharding, persistent TCP connections, replications, quorum, etc., etc. Fair? So Pebble and Rocks will not be able to give you distribution. However, both of them support backup, which essentially means
disk backup kind of.
That's right. Which essentially means you can run a backup at a scheduled time, collect the snapshot, which is a point-in-time data, and move them to a permanent storage. That could be an object storage.
But doesn't it bring a single point of failure?
So that's what I'm saying. When you pick a KV is not distributed. So yes, it will be a single point of failure. However, it's not a database. It's an embedded KV. It is running on top of a database. So database is hiding that detail, right? For example, my Rocks, what does it use for storage? Rocks, right? You still care about distribution, maybe something like a lot of examples, I'm just picking one, Yugabyte, which is distributed, still underneath it is Rocks running on each node.
Makes sense.
And now the questions started coming in fast and thick.
So you mentioned that, like yesterday also, somebody mentioned that NPCI, the scale is 1 lakh requests per second, right? And you guys mentioned that you guys are using Cassandra and you guys have tried out multiple databases. So was it because you wanted to have a cost-effective solution, or you guys found a bottleneck in your write efficiencies and read efficiencies with the similar amount of infra in place?
So if you see NPCI, right, I mean, we are actually running all payment system with 100% open source in it. So most of the dual licensing offerings, right, of any databases, the open source version may not be scalable to the level. And Postgres or maybe Cassandra, and similar to that, there are certain databases which is fully open source. So what we identified is like for our business requirements, right, not just cost matters. So we have to guarantee a latency requirement. Like, I mean, 200 millisecond is our end-to-end business latency, which includes like 21 API calls going between 4 data centers across the country. So, and Sarthak mentioned, right, I mean, our read latency has to be extremely minimal. So our SLA is like 1 millisecond for any read happening on the disk or database. So that is how we categorize it. Any database which we observe that, okay, today we use a technology and we realize that, okay, it can scale to a particular level. Beyond that, we are not able to reach. And the moment we realize it, we start migrating it actually. I mean, today we are using Cassandra, or maybe Cassandra, we removed almost everything from the critical path. And we started understanding that, okay, if it is not Cassandra, today we are using Kafka. Like, what if Kafka reached to that peak point? Can we scale to something else? So we are keep on updating our stack in a way that whatever is the demand coming from the market, right, we should be able to cater to it. So that's only metrics. Cost is not really a metrics. Efficiency is the metrics for us. Like,
but
how we can
there was no
guarantee
such bottleneck that you had to move it from a Postgres to Cassandra or something
So
like that.
Postgres, the biggest problem was our write was not very much optimized actually. And second thing is, if you see UPA, right, it doesn't really require a consistency because it's a message passing system. Your actual bank account or balance belongs to a CBS, which is hosted by a bank. So when you design the system, right, you don't really need to add an overhead to the system, right? I mean, if you don't really need a consistency requirement or anything, so why you really need to use a Postgre database? We can have something which is write optimized, right? We need to have a data stored to ensure that there is a guarantee on data, and if we want to do any operations on top of that, like we do a lot of back office operations or settlements and everything, we need data to be present. So rather than using a consistent database, we can actually go ahead with a write optimized database. That was the choice behind choosing Cassandra. And after a point, we realized that, okay, Cassandra also may not work to that level which we want. So we started using KeyDB. And we even use embedded DB actually. I think someone asked, right? I mean, how you use embedded DB where the data durability is not guaranteed, or maybe the replication is not guaranteed. So identifying the right trade-off is important. So we identified that, okay, certain part, we don't really need a network connectivity or a distribution of data. Rather, we just need a persistence for a short-lived transaction. So we rely on embedded DB to some extent, and we rely on KeyDB. And KeyDB, that too, it's a replicated active-active model. And after that, we write any critical thing into Kafka, and eventually it goes to Cassandra.
To cope up with the speed, does caching help, or persistence is not guaranteed in caching as well, so that is not helping there?
Caching helps actually. So we use caching only as a short-lived transaction. Like I told, right, it's a 200 millisecond. So even to replicate a data between data center or between another node, right, it may take more time actually. Your network latency will kick in. So what we do is like we identify a way where transaction can always, if possible, if the system is active, always land on the same instance or the same application unit where you have an embedded database. So it reads from the embedded database immediately rather than going through a network call. If it is not available, then only it will go to the in-memory database. If it is present in in-memory database, it is good. If it is not present, again, we fall back to Cassandra. So at some point, we guarantee that transaction will be processed, but we take a fair trade-off between from where we should access the data back.
Just a small point on caching, not taking your time. We use the word caching quite casually. Just remember, caching will also, you need to understand whether it needs to be durable or not. For example, let's say Redis says, hey, I'll give you a snapshot. That means it's not guaranteeing durability, right? You have the data in RAM, point in time snapshot, what if it crashes? And same, the other thing with caching is, using caching becomes effective if the cache hit ratio is high, right? I'm trying to search and out of 100 requests, only 5 are finding the keys in cache. It's not a good cache. So with caching, durability will come into picture. It may or may not, depending on the use case. Cache hit ratio becomes more important. If your cache hit ratio is very low, that means only 10% of the requests are finding data in cache, maybe it's just meaningless. Just small note.